Write the numbers from 1 to 10. Now plot the divisors or factors of these numbers underneath and space them out vertically according to their sizes. So the number 1 has only one divisor, itself. The divisors of 2 are 1 and 2. The divisors of 3 are 1 and 3. And notice that the 3 is plotted 3 spaces below the number line. The divisors of 4 are 1, 2, and 4. 5 is prime, so it only has 1 and itself as divisors. 6 is a highly composite number, having more divisors than any smaller number, and so on. A pattern starts to form, and it becomes more interesting as we move farther along the number line. It's easy to spot the primes because they have vertical gaps between 1 and themselves. Now imagine if these divisors could cast shadows from a light shining down on them. If we remove the row of 1s and the diagonal reflection of the number line, the light is able to shine through the gaps. So this pattern serves as a visualization of the sieve of Eratosthenes, one of the oldest algorithms for finding primes. Let's travel further out along the number line and increase the scrolling rate, getting faster and faster, and then stop increasing the rate when it gets to 100. So now the pattern is scrolling rightwards by 100 numbers per animation frame. In other words, real fast. Notice that the larger divisors of 100 appear more stable than the others. Now watch what happens when we bump the scrolling rate up to 101. Poof, there's no stable pattern anymore. But of course, 101 is a prime number. Now at this scrolling rate, it's hard to see everything that's going on. But there is another way to experience these patterns, with our ears. Here's a quick teaser of something I'll be showing you a little later on in the video, a way to express these periodic patterns as polyrhythms. I'll save that for later. I call this pattern the divisor plot. It's like the divisor function, except that instead of showing the number of divisors for each number, it plots the actual divisors on an axis perpendicular to the number line. I made a book about it, and it's available at divisorplot.com. When I came upon this pattern for the first time, I felt as if I were an ancient astronomer trying to make sense of the constellations. I come at all this from the orientation of visual language and perception. For me, this is the most natural way to discover number theory. The pattern kind of reminds me of the patterns formed by crop rows, especially from seen in a speeding car down the highway. This pattern is sometimes called Euclid's orchard. I presented the divisor plot in 2007 at the 7th International Conference on Complex Systems. No surprise, Stephen Wolfram has identified this pattern and published a small version of it. Others have identified and described this pattern, including David Cox and Krzysztof Maslanka. It is closely related to something called the Redheffer matrix. The pattern can be described as the set of points in the xy integer lattice, where x mod y is 0. This pattern can also be generated from a simple geometrical transformation on a grid of points. It's simply a matter of stretching each row of dots out to the right, but the amount of stretching is determined by the position of the row from top to bottom. No explicit numbers are involved here. You could think of it as the residue of a dynamical process. Perhaps instead of obsessing over prime numbers, we should study the total opposite, the highly divisible numbers. They are the ones casting the shadows that expose the primes. If prime numbers are all that is left after you take away the patterns, why not study those patterns? We normally think of numbers in terms of size. For instance, we know that 181 is larger than 180. But in a sense, 180 has a lot more going on than 181. Check out the symmetrical pattern below 180. It's kind of like a complex root system that connects this number to the roots of its neighbors. Notice the twin primes on either side of 180. It's fairly common for twin primes to snuggle up with highly composite numbers. Every number has a unique pattern of divisors hanging below it. And this is related to the fundamental theorem of arithmetic, which reduces this set of divisors to its prime factors. A factorial is the product of all numbers from 1 to n. Factorials are easy to spot in the divisor plot because they have a solid string of divisors at the top and multiples of those divisors hanging below. Would you like to find a chunk of numbers with no primes? Well, choose a factorial, for instance, 7 factorial. The set of divisors highlighted here shows that there are no prime numbers in the neighborhood of 7 factorial, extending out 7 numbers to either side, not including the 2 immediate neighbors, which may be prime. In this case, the neighbor to the left is prime. The 45-degree diagonal feature shown here could be described as a projection of the central vertical divisor line, and it is just one of many similar projections that overlap in dizzying ways. The mother of all divisor lines is the one associated with the number 0. Its projections are all copies of the number line, stretched out and sloped. All divisors come in pairs, as shown in this scrolling view. Let's look at the divisor pairs of 36. They are 1 and 36, 2 and 18, 3 and 12, 4 and 9, and 6 and 6, because 36 is a perfect square. Let's draw a curve that connects all the square roots of the perfect squares. I call this the square root boundary. It splits the divisor plot into 2 regions. These 2 regions have a weird kind of symmetry. This is related to the fact that divisor pairs lie on opposite sides, above and below, the curve. That is, all pairs except for the square roots of perfect squares, which lie on the boundary itself. Now, if we travel along the square root boundary, you may notice what looks like a series of parabolas. Their vertices lie on this boundary, and their arms point leftward. What's up with these parabolas? Let's look at the parabola associated with the perfect square 100. Notice that every number from 0 to 20 is represented in this parabola. Pretty cool, huh? The divisors immediately to the left of the square root 10 are 9 and 11. Their product is 99. Moving leftward, we come to the divisors 8 and 12, whose product is 96. Left of that are the pairs 7 and 13. Now notice that the horizontal distance between each pair is an odd number. Fibonacci made the observation that all square numbers can be constructed as sums of consecutive odd numbers. In the region near a parabola's vertex, we see bilateral symmetry about the horizontal axis. Why is there such strong asymmetry or directionality from left to right? Why are these parabolas all pointing in one direction? Think of these divisor pairs as belonging to rectangular numbers that are more square-like the closer they are to the vertex. If you've ever tried arranging an arbitrary number of objects neatly into a rectangle, you may have noticed that some numbers are easier to arrange than others. If the number of objects is prime, there is simply no way you can fit the objects into the rectangle. And if the number is a perfect square, then it's nice and tidy, just like the vertex of a parabola. So, parabolas can be seen as expressing the idea of divisors approaching squareness. Another property of these parabolas is that each divisor pair in a parabola has the same sum. In the case of the parabola located at the divisor 10, the sum of all divisor pairs is 20. 0 plus 20 is 20. 1 plus 19 is 20. 2 plus 18 is 20, and so on up to the vertex where 10 plus 10 is 20. I refer to this sum as the order of the parabola. But there's more. Look at the next parabola, the parabola of order 21. There is no square root divisor on the vertex of this parabola, just 2 divisors that lie a little bit to the left of the vertex. They have a difference of 1. This is the case for all odd-numbered parabolas. They are associated with the Pronic numbers, also called oblong numbers. These are numbers that have a pair of divisors with a difference of 1. Parabolas alternate between these two types, and they fill the entire divisor plot. But not all parabolas lie on the square root boundary. I was very excited when I found that there are more parabolas hiding in the divisor plot besides the ones that lie on the boundary. For instance, let's look at the number 10368. It's not a square. Its prime factorization is 2 to the 7th times 3 to the 4th, which makes it a powerful number. In a powerful number, all the prime factors are raised to powers greater than 1. Here are the vertices of a pair of parabolas at 10368. Their vertices are located on the divisors 72 and 144, above and below the square root boundary. Notice that 144 is twice the size of 72. These parabolas are associated with rectangular numbers with a 2-to-1 ratio. Another parabola series is associated with rectangular numbers with a 3-to-1 ratio, and so on. Each parabola series lies on a pair of curves that stretch out to infinity. These are called product curves, and I'll explain why in a bit. Now, you may be wondering, what about cube numbers? Well, check out what happens if we scroll through the roots of all the cube numbers. We see something different than parabolas. We see something that looks kind of like cubic curves. Are there other patterns that we might discover if we visit really, really huge numbers? I've explored the divisors of numbers in the range of 9 quintillion. But at this scale, I'm just a mere gnat buzzing around over the Amazon rainforest, so I can't really say if I've missed anything. By the way, did you notice that we have now identified 3 kinds of paths through the divisor plot? First, there are the divisor lines originating from the number 0, each of which contain every natural number. Then we have the product curves, which also contain every natural number, but they contain different sets of divisors than the 0 lines. And we also have the square root parabolas, which contain all numbers from 0 to n, with n being the order of the parabola. I call these divisor curves. They show a hidden structure in the number line that we don't see in one dimension. Every divisor lies at the intersection of 3 curves representing each family. You may be familiar with the Ulam spiral, which provides a cool way to see patterns in prime numbers. But it's really not a spiral. Robert Sachs identified an Archimedean spiral that reveals the primes in a new way, and it's more elegant than the Ulam spiral in a sense. It wraps around so that all the square numbers line up on a straight line. In the Sachs spiral, prime numbers tend to lie along curves that sweep leftward. Analogous to the divisor function, which counts the number of divisors of each number, the Sachs spiral can show these values using color, as shown here. Sachs identified several curves that cut through the spiral arms in various ways. These curves are associated with divisor pairs that have a fixed distance. He calls these product curves. And here's why I use that term for the curves I showed you earlier. When I showed Robert Sachs the divisor plot, he identified some features that it has in common with the spiral. Most notable are the product curves. Check out how the product curves map between the spiral and the divisor plot. Let's highlight the first product curve in both the spiral and the divisor plot, the one containing the perfect squares. Is there a way to match up these two curves? Well, watch as I take the divisor plot, flip it upside down, and then roll it onto the spiral. This is a transformation that stretches the divisor plot exponentially so that it can be attached to the Sachs spiral. Now we can plot the first few product curves in the Sachs spiral in 3D. And here's an animation scrolling through the even and odd-numbered square root parabolas. Conjecture. The music of the primes has no rhythm. All the rhythm is in the composite numbers. Let's bring in the element of time and express numbers not as dots on a screen, but as sound points. Our ears are able to pick up temporal patterns that are not so easy using our eyes. Let's attach a voice to the first divisor. Think of this voice as a tape head in an audio tape recorder. Now let's start scrolling. If we play the number 1 like a musical score, we get the simplest possible rhythm. If we play 1 and 2, we get a period 2 rhythm. If we play 1, 2, and 3, we start to get an interesting syncopation. It's a polyrhythm with a period of 6, because 6 is the least common multiple of 1, 2, and 3. Now check out this polyrhythm played by 6 toy monkeys. Each toy monkey plays a regular beat, but each beat is different. They include every period from 1 to 6. Now, if we plot their sound points along the axis of time, we see that there is another way to generate the divisor plot, as the residue of a polyrhythm. Here's a very unsyncopated polyrhythm, performed by the powers of 2. What happens if you play only prime divisors? Well, I asked myself that very question, and this led me to the discovery of a class of numbers called primorials. A primorial is like a factorial, but instead of being the product of the first n numbers, it is the product of the first n primes. If you multiply all the primes up to and including 41, you get a number that is a little over 300 trillion. Here's what it sounds like when I play all prime divisors from 2 to 41 with a fast scrolling rate. I call this primorial chaos. Our ears cannot detect any pattern. This cycle will not repeat for over 300 trillion beats. Now check out this musical composition. I'm not the composer. The composer is 12 factorial, the product of every number from 1 to 12. Now, listen to what happens as we approach the very special number 12 factorial. Ready? It's as if we had 12 monkeys, each playing a different beat, and they all played at the exact same time. A rare event indeed. By placing voices on select divisors and making them play different sounds when the divisor passes by, we can construct a kind of a mathematical drum machine. Here are some examples of polyrhythms made with this process. The patterns formed by plotting the divisors of composite numbers provide a playground where you can engage your pattern-finding instincts. In the process, you might discover some cool concepts in number theory, as I have, and the discoveries just keep coming. Internalizing these patterns using our eyes and our ears can help us gain intuition in number theory. And this is complementary and fully compatible with representations that use math notation.